and not case number 2, but what we're going to be looking at, the last thing is that we're going to be looking at inelastic collisions. And in this scenario here, there are two things that happen. There's two possibilities. So two possibilities here. And what you find here is that you get the following thing. What you find here is that one case here, you get what's known as completely inelastic. And then the other case here is known as just inelastic. And it's the inelastic one that you want to be careful about. And so this is what happens here. So you could imagine that you send in a block and it's coming in, and there's a stationary block. It doesn't have to be stationary, but what we're assuming here is that when I look at 1 versus 2, I know that 2 here is going to have, let's say, starts off with an initial momentum of 0. And then afterwards, what literally happens is that these two blocks get stuck to each other. And as they get stuck to each other, they move together away as one block. So I can literally replace them. And what you're going to see here is that they're going to have some final momentum that's a combination of 1 and 2. In elastic, well, it depends on the situation, but you have a block that comes in, and maybe you have a second block. Let's say again that this guy starts off from rest here. And what you're going to find in this situation is that there's a collision. And it's much harder to say what is actually happening in this case. But all we know in the end is that this guy's moving like that, and this other one is moving, let's say, like this. And the thing that's special about this is that there is no energy conservation. And there are three possibilities. One, we talked about completely inelastic. That means an object comes in, it hits another object, and they stick together afterwards. Or I could have inelastic. That means they come in, they hit, and they could either go forward direction or they could bounce back. And there's a third one, which is one that it's inelastic, where the projectile goes through the target. So in this case, what am I actually seeing here? Well, what I have here is that you can imagine I have my block, but this time instead of having a block, I'm going to say that I have a little bullet-like thing here. Okay, so I have a bullet, and what you're seeing here is that this guy is object number 1. So that means it has what? It has momentum coming in. And what it's going to do now is it's going to hit a block. So when I look at this guy here, what you're going to find here is that if this guy starts off at some initial momentum, afterwards, what happens here is that I continue to have block 2 there, But what you're finding this time is that this thing then moves with some final momentum in that direction. On the other hand, the bullet's trajectory here afterwards has a lower momentum moving in that direction right there. So what's special about each of these three cases? So when I look at the system, let's say I only look at one of them. If I look at my system, let's say that this is my system. What you're seeing here is that in this system, the forces are internal, okay? There's internal forces, so therefore the impulse is zero. So in this case, that the enclosed system only has internal forces. So in this case, I have equal and opposite impulses. So therefore, this immediately tells us that since the external impulse is zero, then the total momentum before is equal to the total momentum afterwards. That's beautiful, right? No problem. However, energy is not conserved. And the reason is this here, is that the forces during the tunneling process are non-conservative, which implies that some of the energy is lost to the environment as heat. So you can't track all of the energies. And as a consequence, what you're seeing here is that now the kinetic energy beforehand is not equal to the kinetic energy afterwards. So the key signature of inelastic collisions is that the energy is not conserved. And there's lots of examples of this thing here. So just as another example here would be a bouncing golf ball. So you could imagine that I have a golf ball, and we imagine that, let's say that this is my golf ball right here. And if it has a collision with the floor here, right? Let's say this is the floor. What you're going to find here is that if I make my system to be the floor and the golf ball, what you're going to find here is that this golf ball is going to do what? It's going to come all the way down here to the bottom, right? It comes all the way down here to the bottom. And right before it hits the ground, it's going to have some momentum going in this direction. So according to conservation of momentum, what you're going to find here is that the ball afterwards is then going to have a final momentum going in this direction, but in the opposite direction, the so-called Earth must be moving with the momentum in the opposite direction. Momentum is conserved. Would it be easy to measure the momentum of the Earth? Of course not. It would be hard. But what you're finding here is that if I look at this from the energy standpoint, you know it's not non-conservative. So momentum-wise, it is conserved. Now, if I look at it from the viewpoint of energy, this is what we would see here. Here's the ground. The ball starts up here. The ball comes down to here. And then what we know here is that it goes through a compression process. And then during that compression process, the ball then comes back up. And then finally, it gets to this point right here. So let's look at this thing in detail. So here's the moment. So we know that this thing starts off at some height y1. When it gets right before it gets to the bottom, we know that it has some speed, v1 initial. And of course, v1 initial in this case is the same as that scenario right here. But then what happens here is that the ground is doing work on the ball. And what does it do? It compresses the ball. And what you're seeing here is that during this process right here, there's heating up of the ball because of the compression. So then what happens? The ball comes up and it goes, and what you're seeing here is that when it leaves, it has a smaller velocity now. And as a consequence, it goes up to a lower height. So the fact that y1 is not equal to y2 implies that work by the ground on the ball is not conservative. And if it's not conservative, then that implies energy is not conserved. That is a sure statement of conservation of energy not working in this scenario. Therefore, we call that an inelastic collision.